Hi, my name is Austin Cox and this is homework 4, part B1. And here we will be taking the process transfer function for the liquid level in the third tank of 3 tanks in series. And this is our process transfer function k over tau s plus 1 cubed. And here we'll be drawing the block diagram for this process, in which it is under a feedback control with a proportional only controller with a controller gain kc, and we will then derive the closed loop transfer function relating the level in the third tank to the height set point. All right, so moving into our transfer function, we can move into our block diagram. So our transfer function, we put a box around it, and we can denote this our GP. So we'll have some input going in, and from our GP, we will output a height. And from this height, we know that we have a feedback control loop. So we will go from here, and in our feedback control loop we have some measurement device, and we can call this our GM. And then moving up from our measurement device, we will move into a comparator, and from here we will get our error of our process, and from our error we will go into our KC, which is our controller gain, and this KC term here we can denote as our GC, and then that will return back into our process transfer function. And initially what we need to send into our function is what our height set point is. So we can write that as HSP. So we're given some height set point, and we have a proportional only controller, and then it is being sent into our process transfer function for the height of our third tank. And before we are given the output, it is going to be measured and then returned into the comparator, and then it will be buffered from there, and then eventually we'll get the height. So our height here, we know that H is going to be equal to our error times our GC times our GP. So we can write error times GC times GP. And our error here is going to be our height set point minus our actual height. So we can write epsilon is equal to HSP minus H. So go ahead and replacing this into our height expression, we get that H is going to be equal to our HSP minus H, and then this will be times GC times GP. And doing some simple algebra, we can write that our height is going to be equal to HSP times GC times GP, subtracting our H, GC, GP. So now what we want to do is isolate our H and our HSP so that we can get an expression for our respected heights. So doing so, we can add this over. So we'll get H, GC, GP plus H is equal to H, SP, GC, GP. And then taking out our height, we can get H, GC, GP plus 1. And then we can divide our GC times GP over here. And after moving this term over to here to our denominator, this is going to be equal to our HSP. So now that we have our H and our height set point on their own respected sides, we can now go ahead and get an expression for just our height. So doing so, I'm going to move over here. So our height is going to be equal to, and when we're moving this fraction over, we're going to flip it, because you multiply by the reciprocal. So our height is going to be equal to GC times GP, and this will be over 1 plus GC GP. And then lastly, it'll be multiplied by our height set point. And for our closed loop function here, we are not taking into account for our GM, our measurement device. For this scenario, we're just going to say that our GM is equal to 1. And if we were to incorporate it, it would end up in our denominator, multiplying GC times GP times the GM. So now what we're going to do is we are going to define what our height set point is going to be. So for this scenario, we can draw a little graph for our X and Y. In our Y-axis here, we're going to call our height set point at some position. So we are initially going to start at some value, and at time t, we are going to have a step change, and then that is how our process will move forward. And the step change is going to have an amplitude of A. So our height set point here, HSP, is going to be equal to a step change, and the Laplace transform of a step change is the amplitude over S. So now what we're going to do is go ahead and plug in our values for our GC, GP, and our height set point. So doing so gives us that our height is going to be equal to our GC is KC, our GP is K over tau S plus 1 cubed, and then this will be over 1 plus KC K over tau S plus 1 cubed. And then this term here will be multiplied by our A over S. Alright, so now that we have this expression here, we now need to get a common denominator so that we can simplify our expression here. So we have a 1, and the rest of the denominators we have tau S plus 1 cubed. So what we're going to do is transform this 1 into tau S plus 1 cubed over tau S plus 1 cubed. And then you can see that all of our denominators here will cancel out. So then we are left with our height being equal to our controller gain Kc multiplied by our process transfer function, which is going to be K, and then we will be left in our denominator a tau S plus 1 cubed, and this will be plus KCK, and then again multiplying by our step change for our height set point, which is A over S. Okay, so now our next step here is going to be expanding our tau S plus 1 cubed in our denominator. So do that over here. Tau S plus 1 cubed is going to be equal to tau cubed times S cubed, and this will be plus 3 tau squared S squared, and then we will be adding 3 tau S, and then lastly 1 cubed is going to be equal to 1. So this is the expanded cubic of our tau S plus 1 cubed. Okay, so now that we have expanded it, we can go ahead and return it back into our closed loop transfer function for our height. So our height here is going to be equal to KCK all over tau cubed S cubed plus 3 tau squared S squared plus 3 tau S plus 1. and this will all, and additionally plus KCK. And then this will be multiplied by our step change again, A over S. I'm going to go ahead and put our A in the numerator and multiply our entire denominator by S. So this is our closed loop transfer function in order to determine the height of the third tank based on the our GP of K over tau S plus 1 cubed. Hi, this is homework 4, part B2. And in our previous part, we had derived the closed loop transfer function to determine what the height of our level in the third tank will be. For this part, we will be using the Routh-Hurwitz criterion, and I have that the general scenario for the Routh-Hurwitz over here on the right. And what the Routh-Hurwitz criterion is, it allows you to determine the maximum values in which your process will still yield or still remain in stability. So we can go ahead and dive in, beginning our analysis. So our a to the n term is going to be tau cubed. Next, our a to the n minus 1 is going to be 3 tau squared. And then our a to the n minus 2 is going to be 3 tau. And then our a to the n minus 3 is going to be 1 plus kck. And then for just this scenario here, our values on the right are going to be 0 and 0. So next what we need to do is calculate our B1. So our B1 is going to be equal to a to the n minus 1, which is 3 tau squared. And then this will be multiplied a to the n minus 2, 3 tau. And then we will subtract a to the n, which is tau cubed. And then multiply this by a to the n minus 3, which is 1 plus kck. And then this will all be over a to the n minus 1, which is 3 tau squared. So you can notice that we have 3 tau squared and 3 tau squared in the numerator and denominator, so this can go ahead and cancel out. And then this tau squared will also pull off, it'll also pull off this cubed, and it'll make it just t to the first power. So our B1, we can write it over here, is going to be equal to 3 tau minus tau times 1 plus kck, and this is all over, or sorry, just this part is going to be over 3. So for our, that's our B1. Okay, now that we have our B1 term here, we now want to determine what our second B term is going to be. And that is going to be this times that, and then we'll be subtracting this times that. And if you notice from that expression, our B2 term will yield a 0. Okay, so now that we have our B1 term, we now need to determine what our C1 term will be. So we can write that C1 is going to be equal to B1, and then this will be times a to the n minus 2, which is 1 plus kck, and then this is subtracting 3 tau squared, and then this will be multiplying by b, which b2, which is 0, and then this is going to be divided by b to the n, which is going to be our b to the 1. So you can see that we have B1 in the numerator and denominator. So we can go ahead and cancel those out. And then our 3 tau squared is multiplying by 0. So for our C1, we will be left with 1 plus KCK. And then for our C2 term, similarly, we will end up with 0. And the criterion for stability is that, for the Routh-Hurwitz, is that we need everything in this first column here to be greater than 0. So we look at tau first. Tau is our time constant, so that will always remain positive. So our first two terms meet the criterion. We move into our third term. We have our tau again. However, we are subtracting tau times 1 plus kck. So this is going to be our determining coefficient for the criterion analysis. So moving forward, we can write that 3 tau minus 1 plus kck times tau, and this over 3. We need to determine which scenario and which expression will yield the maximum value of the kc in this scenario. So we want to write that this must be greater than 0. In order to simplify this, we can move this over to the right side, which will give us 3 tau is going to be greater than 1 plus kck times tau over 3. So now to simplify this more, we can multiply by 3 over tau. In doing so, cancels the 3 in the denominator here and the tau in the numerator. So then we will move over here again, multiplying by 3 over tau. Our tau's cancel, and we are left with 9 is greater than 1 plus kck. Okay, so continuing on, we have 9 is going to be greater than 1 plus kck. Subtracting 1, we get 8 is going to be greater than kc, and we can go ahead and move the k over so that we can determine our limits for which are kc. So we have that 8 over k must be greater than kc in order for our scenario to always yield a stable solution. And here we are assuming that k is going to be greater than 0. We will now move into Google Colaboratory using Python in order to prove that this determining factor is going to actually yield stability or not.
Hi, this is homework 4, part B3. Here we will be confirming our result from our Routh-Hurwitz stability analysis, and we will be running a simulation for k value of 12, tau equal to 1.2, and we will simulate this response in step change increase and set point of 0.12. So now we can go into Google Colab and go ahead and code this out. So we're in our part A code. We can now add part B to this, and I'm going to hashtag that in. This is B. All right, so for part B, we can begin with putting that our k value is going to be equal to 12. And k is equal to 12. Our tau is equal to 1.2. And we can denote A for our step change is going to be equal to 0.12. Okay. So next, we can go ahead and write what our GP is. And our GP here is going to be our process transfer function that we had in part B. It's for the third tank response, it's going to be K over tau s plus 1 cubed. So we have K over tau times s plus 1, and this value is going to be cubed. Close that off. And our s here, we are using simpy.abc. We're importing s, so that is going to display as a symbol s, sort of like the variable. So next, our gc, we can start initially with this at 0.1, and this term is our kc value, in which we are changing, in which we had previously derived that the maximum value is going to be 8 over k. So next we need to define what our closed loop transfer function is going to be, and we can use the shortcut here. So we can write that our loop expression is going to be our GC times our GP. It's everything that's in the forward direction, and then it's going to be divided by 1 plus GC times GP. All right, let's do. And just to display what our GP looks like, I can go ahead and print that. So it's simplifying it, but we should have 12 over 1.2 s plus 1 cubed. And it is just giving us this decimal because it is dividing the numerator by the 1.2. Go ahead and get rid of that. Shift and enter. Okay, so next we want to go ahead and run our simulation. And for our variables here, our y-axis is going to be the height, and our x-axis is going to be time. So we want to go t, comma h, and we want to use our sim function, and we want to, our closed loop system is our loop function. Our u here, we are going to create an anonymous function, and we're going to use lambda and t, and then for this function we are going to call our step, which is our a, and then next we can define our number of steps here, and we can just go with 1,000, and then lastly our time steps, our dt, we can just keep that dt is equal to 1. Right, so that's for our simulation. Go ahead and shift enter. All right, that looks good. So next what we want to do is go ahead and make our plot for this scenario in which we are running the simulation for our closed loop function, which will allow us to determine the liquid level of the height in our third tank in series. So you can go with fig is equal to make underscore subplots, and then we can go fig dot underscore scatter. Our x here is going to be equal to our time. Y is going to be equal to h. If we want to name this, we can go ahead and name it height of third tank. And then lastly, we can do updating our layout. We can make our width equal to 800, our height equal to 600, and then template here, we are going to do seaborn. Got some nice colors on it. All right, so let's go ahead and see what this graph looks like for our GC value of 0.1. Shift enter. Okay, so you can see that it is a stable system. It is initially sparking up and then going back down, and it is reaching steady state fairly quick. So now we can go to 0.5, shift enter. So now we're starting to see some oscillations in our simulation. So now what we want to do is test out 0.66. So we had previously derived that the maximum value is 8 over k, and for for this simulation here, our k value is 12. So 8 over 12, the maximum value is going to be 2/3. So this 0.66 is going to be just under the cusp of stability. And you can see that by this plot here. It is initially starting very up and down, and however, it is still reaching some steady state. So let's see what our derived value will give us, which was 8 over k. So this is really nice. This is right on the cusp of stability. It can't be greater than this value here. So let's see what happens when we add to that. And this is the scenario that will break our system here. You can see our y-axis, we are at 10 to the 16 in the positive as well as the negative. Let's just go back to 0.6. Yep, so this proves that our derivation in the previous part is correct for the scenario in which we cannot exceed 8 over k for our kc value. Thanks for watching.